Nowadays, whenever I talk to anybody, particularly students coming to UCL, I feel very guilty when I'm not talking about deep neural networks. I have this terrible insecurity that crops up inside of me. So unfortunately, I'm not going to talk precisely about deep neural networks today, but I guess, people are telling me, Herbster, you're telling me when you're doing this project over the summer, you need to do this feature engineering, deep neural networks. You don't need the feature engineering. Forget about it. The deep net, intermediate layers, you got your features. Forget about it. And this makes me very insecure. But at least, I guess I'm going to try to argue, at least in some sense, one of the take-home messages, in some sense, with you can get away without feature engineering. You can get away without kernels in at least in some weak sense, which I'll argue in the online setting eventually. This is based on some previous work, not by this name. I just thought I'd have this name to reflect my insecurity today. Okay. So what are we going to do today? Well, we're going to give an algorithm for online matrix completion based on matrix winnow, matrix exponentiated gradient descent, which is connected to mirror descent methods, which we've heard about this morning. For the setting, I think we'll give some of the first mistake bounds in terms of the margin complexity of the matrix. And we'll give an interpretation of margin complexity bounds in terms of kind of two setups, multitask prediction and biclustered matrix prediction. Okay. So what do I mean by online matrix completion? We're going to just consider a very simple setting. We have some m by n matrix. It's going to have either a plus or a minus in each cell of the matrix. We won't know this matrix. We'll know the dimensions ahead of time. And then we'll play some game over some number of trials. Through some process, which I'll call nature, the learner's given an entry of the matrix, IT, JT, time t, and we're asked to go ahead and predict that entry. It's a binary prediction game. Learner will predict -1 or 1. We'll get the true label for that matrix. And our goal is to minimize mistakes. That's all we care about. Very simple setup. And so what we're looking for, kind of very easy bound to get a bound m times n. But hopefully, if there's something somehow simple about the underlying matrix which we're predicting, we shouldn't make many mistakes. Now, because I want to make my life simple, I want simple slides, there are, we could kind of move this to a regret setting, and we would get slightly more complex bounds. But to keep things simple, we're going to assume that there exists an underlying labeling of the setting, and we want to get bounds in terms of the complexity of the matrix. Okay. So what's a natural complexity for a matrix of pluses and minuses? Well, one natural thing would be what's called the margin complexity. Now, you're used to thinking of matrix completion as, you're trying to do well when there's low-rank matrices which explain the data. So how do we define margin complexity? Well, we look at our matrix of pluses and minuses, and what we're looking for is we're looking for a factorization of this matrix into matrices P and Q. Here's P. We have vectors which are k-dimensional in P, 1 through m of them, n vectors in Q, which are also k-dimensional. And the margin complexity is, given our matrix P and Q, we choose the matrix, the best factorization, such that this term is minimized, where we pay for the worst norm in P and the worst norm in Q via the 2 norm. If we got rid of this last term, we would just be writing down the max norm. Adding this other term is we're basically saying, look, we don't have to make these precisely +1 or -1. We're allowed some margin. This gives us a bit more flexibility. If I made this equal sign here, we'd have the max norm, and this would potentially be much larger than if we allow this inequality.
So this is just saying PQ transpose and U are of the virtually of the same sign?
Yeah.
Okay.
Yeah. So what we're looking for is when we take, say, PM dot with Q1 here, we're looking for this value to be +1 or larger.
Okay.
-1 or smaller. Okay. Margin complexity. The algorithm which we're going to use, variant of the exponentiated gradient algorithm, or WINO. We're going to take a matrix, because we're going to, somehow our life's going to be easier if we're working with positive definite matrices. We're going to symmetrize our matrix, so we have a matrix of m plus n dimensions. When we get a pair, we want to go ahead and predict an entry, make things kind of work smoothly. We have this symmetrization here, and then we just have a simple threshold prediction. We look at our hypothesis matrix, we predict the element, and we predict +1 or -1, and then we update where this is the matrix log and the matrix exponential. So whenever we make a mistake, unfortunately the algorithm isn't as efficient as one might like. You know, essentially we're doing an SVD on every step to make our update. We won't go through the proof, but what we show in the paper is that in this setting, we can show that our algorithm, if there exists some underlying matrix U, the number of mistakes that we make scale with the square of the margin complexity, the dimensionality of the matrix, and an additional log term. We also argue in the paper, which we'll do today briefly, that the bound is tight up to a logarithmic factor in the following sense. We'll say, given any online algorithm A, and somebody tells me some constant L, then there exists some matrix with margin complexity squared less than L, and a sequence of matrix entries that an adversary gives to us such that the algorithm is forced to make at least L times n mistakes. Okay. So here we're matching this up to a logarithmic factor. Just a technical slide up. There are some previous results on online matrix completion in a regret setting for more general loss functions, a bit more complex algorithms, taking a bit more computation time. Just a brief comparison. One thing nice about our bound is these bounds, at least to become meaningful, you have to see at least n to the 3/2 samples for 4, at least n to the 7/4 to be non-trivial. Whereas, because in fact there are fairly natural classes of matrices with small margin complexity, we need order n, where I'm using twiddle-o to suppress logarithmic factors to be non-trivial. Okay, let's look at a couple of examples for interpreting the bound. Okay, suppose somebody handed me a kernel, where I think of a kernel as something which is giving me a similarity between items in some space. So in the online setting, Blue maybe wishes to predict, or we wish to predict which films Blue might like. And if somebody gave us some form of similarity in advance, some kernel function on films, we might, through very simplistic online algorithms, go ahead and play an online game trying to predict what films Blue likes or doesn't like. So we can think of this as a single task. We're just playing an online game where Blue gets queried whether she likes a film or not, and we try to predict that. So right now, rather than predicting the entries of the matrix, we're predicting the entries of a vector. So here, learning proceeds, and same setup as before. Learning proceeds in trials. Rather than getting an entry of a matrix, we get an index of the vector. We go ahead and we predict a Boolean entry. We return true or not, and we make a mistake or not. And so in this setting, classic result gives us a bound for this problem. If somebody handed me a kernel in advance on the movies, I could apply the kernel perceptron. And there I would just make some bound, which is just something like the product of the margin times the radius of the space in which the data lives. Quite straightforward. There's many online algorithms which perhaps are designed to improve on the kernel perceptron in some way, but in some sense, in a lot of settings, you can't really beat the Novikov bound, I would claim. Okay. Suppose we didn't have the kernel in advance and we wanted to do well. I should point out, when most people use kernel items, it's not that somebody just hands you a kernel. Instead of being handed a kernel, a typical scenario is that you're going to be handed, say, a Gaussian kernel, and you're going to have side information associated with each element you want to predict. So you have your Gaussian kernel, and you have some vector in Rn, which you're using to help you work with that side information. What we want to argue now is, in some sense, we don't need the side information. We don't need the kernel in advance. And the way we're going to be able to get away with this is we're going to have multiple tasks. So now we have Blue, and we have Osmo, and Georgina, and Flo, for instance. And they all would like to, we wanted to play this game with them. But we're not going to have the kernel. But in some sense, we can predict as well as the best kernel without knowing it. Each task is now going to correspond to a row in that previous matrix prediction problem. I think I didn't write a long enough talk today. So things come very quickly. Perhaps it's not surprising from our previous definition of margin complexity that we can rewrite margin complexity in the following form. We have the margin complexity squared is the result of this minimization over all n by n PSD matrices such that we choose any arbitrary vectors in Rn. We maximize this quantity with this given constraint. That's just another way of writing our previous definition of margin complexity. Which perhaps isn't surprising. We're somehow taking the P and Q and incorporating them both into K. I think I keep wanting to jump around slides. So recall our previous bound for predicting the elements of a matrix is just depended on this margin complexity squared, and then we had the remaining terms. This term is the margin complexity, and this term should look familiar. This is just, if we just look at this part, we're just pulling out the parts of Novikov's theorem before. This is just the margin. This is just the radius the space lives in. And so what are we doing when we use matrix winnow? We're predicting, as well as the best possible kernel. We have the maximum here over on the hardest task. Okay. Okay, so this part is unpublished. Hopefully there isn't a mistake here, but hopefully publish this soon. We can improve that uniform bound to the following non-uniform bound. Once more, we get to choose the best possible kernel. Rather than paying for the worst possible task, we have our M tasks, where we're predicting n items. Now, each task we pay relative to the complexity of that task, not the worst possible task. The max is just over to find the radius of the space. One wanted to, one could take a normalized kernel and get rid of this term. Price we're paying is we incorporate this additional n squared term, which is basically saying our bound is going to be vacuous if we have many data items and few tasks, but if instead we have lots of tasks, smaller number of data items, is when the bound has some meaning. Okay? So we have a lot of tasks and the number of items is fewer than the number of tasks. The bound is non-vacuous. So in this sense, forget about side information on your task. Forget about a kernel on your side information. We don't know it. If we have enough tasks compared to the amount of items, we don't need to know that kernel in advance. Okay. Okay. Another simple plug-in result for the margin complexity. Lots of time. Okay. Biclustered matrices. So perhaps, really, I think it's a fun hypothesis class over matrices. I'm not really clear on what other results are out there for it. I think it's fairly popular in practice, but here we go. So biclustered matrix, we say a matrix is biclustered if KL biclustered, if after a permutation of the rows and columns, if there exists some permutation of the rows and columns such that this turns into a KL grid of rectangles, each of these rectangles uniformly labeled as either -1 or 1. It's kind of hard to tell by eye that this is a 9×9 biclustered matrix. I'll let you take my word for it. Just a simpler example so you get the idea. 2×2 biclustered matrix. So what I'm saying is we permute the rows, we permute the columns, we can turn it into a set of rectangles here. They worked out into a checkerboard pattern, but these three could have been orange and that could have been blue, for instance. Okay, another way to think about the hypothesis class of biclustered matrices, forgetting about permutations, is we have some latent variable on the rows, we have some latent variable on the columns. The latent variable on the rows can be in one of k possible states. The latent variable on the column can be in one of L possible states. There's some underlying function which maps k, L into +1 or -1, and that determines our labeling. Not too bad to show that the squared margin complexity of a KL biclustered matrix is less than the minimum, or k times L. Given this internal matrix F, it's not difficult to see that the VC dimension of BMKL is lower bounded by k times L. And so combining this observation, if you have a hypothesis class with VC dimension, that's always a lower bound in the mistake-bound model. And so combining these two things, that is essentially the proof of our fairly trivial lower bound that we showed before. Very fast talk. Okay, these are some useful references. Thank you.